Good morning. I would like to thank Richard and the Simons Foundation for giving me the opportunity to talk here. So what I would like to tell you today about is our efforts to model at the microscopic level the energy and spatial landscape that energy and charge carriers explore in semiconducting materials. So I will talk about both molecular organic crystals and hybrid lead-halide perovskite, with trying to answer that question about how soft those materials are. And of course, this is implication for transport, as we've just seen, and can be pictured nicely, I think, with this ball on a matrix motion. Of course, the softness of the material will actually dictate the interaction from strong interactions to weak interactions, and therefore also the charge carrier mobility or exciton diffusion that you can reach in those materials. So let me start. Okay, well, first, when you think about organic materials, I will start with organic systems. You tend to think that these are really soft materials, and their disorder is ubiquitous, as we just discussed. There's hardly any long-range order. We are talking about very weak interaction between molecular units. So that gives rise to Anderson localization or dynamic localization because of coupling to all sorts of phonons. In contrast with inorganics that should sustain delocalized states, extended states, delocalized wave functions, and give rise to much higher charge carrier mobility. So I will change a little bit this picture, starting with organics and discussing in a very simple term how we can picture this from a model Hamiltonian before going to atomistic simulations. So, as has been discussed, in principle, if you have an organic single crystal, you can think that in those systems you have translational symmetry and so extended states. But what happens in reality is that those molecules are not fixed in space. They fluctuate in their relative position with respect to the equilibrium geometries, and that gives rise to change in both the site energies. The energy of a site, of a charge sitting on a molecule, will fluctuate in time, and in the quantum mechanical coupling between neighboring molecules. And that drives self-localization into one molecule in the case of a system where transport is driven by hopping and is thermally activated. Now, I would like to derive a model that is able to capture the two worlds, going from hopping to a band-type transport. And this is a work that has been done by Lin-Jun Wang in our group 5 years ago, looking at model Hamiltonians. So this is a simple one-dimensional model. And we have coupling to a couple of vibrational modes that give rise to fluctuations in the site energy. That's called the local electron-phonon coupling, and in the transfer interval, that's called the non-local electron-phonon couplings. And to solve the problem really carefully, you need to solve simultaneously the equation of motions for the electrons and the nuclei, and we're trying to simplify the problem to treat the electrons in a quantum mechanical way and the nuclei in a classical way. And that gives rise to an approach that has been developed by Tully a number of years ago. It's called a fewer switch surface hopping model, which you will hear in more detail from Jochen this afternoon. But so essentially we're using this model Hamiltonian, and what it gives, is the charge carrier mobility along this one-dimensional stack, which are good models for one-dimensional transport in organic crystals. And we can predict the mobility versus temperature as a function of the quantum mechanical interactions. So that's the parameter. Tau here is a measure of it's a transfer interval, is a measure of how strong the molecules interact quantum mechanically with one another. So if you have weak coupling between the molecule, you get temperature-dependent, temperature-activated behavior, hopping like a transport. If you go to much higher interaction between the molecules, you tend towards a polar law behavior for the mobility that decreases when you increase the temperature because you have more scattering with the phonons. At the same time, that's interesting, we can track the amount of, the localization length of the charge carrier, and you can see that in the localized picture. it's confined over a single unit, a single molecule, a single site. But what is interesting is that, and this is reminiscent, of course, of the transient localization model that we've just heard, that you don't really need the state to be delocalized over the entire crystal to get to something that looks like band-like transport. You only need a few molecules, here 3 to 4 in that model, to get band-like transport in terms of the temperature dependence at least. And so the delocalization length is a good proxy in a way for the charge carrier mobility. Now, this is for a model Hamiltonian, and is it possible to do this for real atomistic structures? The answer is yes, and you will have to wait for your presentation this afternoon to know more about this. But what I would like to do is tell you something about the different ingredients that would enter into the Hamiltonian that we need to solve. One ingredient that we have worked a lot on recently is electrostatics. So, and this is best captured if we take the electronic structure of a single crystal of pentacene or perfluoropentacene. So these are highly polarizable molecules. So when you put a charge, and suppose a charge is sitting on a single molecule, it will of course fill the environment, and will fill in the environment in different ways. First, it will create induced dipoles in the surrounding, and these induced dipoles will interact with the charge, stabilizing the charge. And that's why if you compare the gas phase molecule to the solid, there is usually a huge, talking about something like 2 electron volt, reduction in the band gap going from the gas phase to the crystal. And you can see the blue lines here are the theoretical simulations. Without going into the detail, you can go to really highly accurate techniques nowadays to predict those numbers. There's another effect, which is just the interaction between the charge sitting on the molecule and the surrounding neutron molecules. So that's purely charge, multiple moment interactions, charge quadrupole interactions mostly in those systems. And this will shift the energy levels, in this case, up for pentacene. But if you take perfluoropentacene, you see that the same charge quadrupole interaction then shift the energy levels down. And this is the band dispersion, quantum mechanical interaction between the molecule. And then you can compare to experiment, and it seems to work quite well. So the opposite change in the energy levels due to the charge quadrupole interaction simply reflects the fact that in those molecules the quadrupole moment is reverted because of the strong CF fluorination effects, withdrawing groups compared to the CH groups in the pentacene molecule. And you can push this a little bit further by looking at co-crystal of the molecules made of pentacene and perfluoropentacene, and you can make those co-crystals in a one-to-one composition, and they adopt this nice alternated structure with pentacene, perfluoropentacene in a sandwich-like configuration. And if you look at the UPS data of those co-crystals, while you would expect that in the mixed film you would have something that is intermediate, that is the superposition of the two molecules, which are shown here in blue and red, what actually you see is something that has a twin peak at intermediate position between the two. So the energy levels of those molecules does not only depend on the molecules themselves, but strongly depend as well on their environment, especially the electrostatic environment. This is very nicely captured by the model. You can see this twin peak in the middle, and this is entirely driven by the interaction of the charge with the surrounding quadrupole moment with the electrostatic environment. So that will, of course, dictate the absolute values of the energy levels, but possibly also the fluctuations, because as the molecules move around the equilibrium position, that will contribute to some, that will add some contribution to the energetic disorder. It has implications also for doping. For instance, we looked at p-doped material. Host molecules like pentacene and alpha NPD can be doped with a strong electron withdrawing molecule like F40CNQ or F60CNQ, shown here. And I mean, the picture is very simple in principle. You would expect that if the LUMO energy levels of F40CNQ or the dopant is below the HOMO energy of the host, then you can have a full charge transfer in the ground state, and that gives rise to an ionized dopant and a hole sitting on the pentacene. The hole, the excess charge, the excess positive charge can move in the organic semiconductor and could contribute to to conductivity. Well, this simple cartoon has to be really taken care, has to be considered with caution, because in reality, the energy level of the dopant, the LUMO level of the dopant, turns out to be very different if you look at the energy level of the dopant in its own environment. So if you measure the electron affinity of the F40CNQ, for instance, in a pure F40CNQ film, or if you measure it in the host material. And typically, the typical behavior is that this energy level, in the case of F40CNQ or F60CNQ, shifts up. So the electron affinity of the molecule is strongly reduced when you move the F40CNQ from its own environment to the whole transporting material. And now, while initially you would expect that there would be a full ground state charge transfer from the simple picture, now the energy level of the F40CNQ in its environment shifts from this position to somewhere here. Now it becomes impossible in principle to ionize the host solid. Well, yes and no, because there's something that's, and this is entirely due to electrostatic again. Well, yes and no, because there's one thing that we're ignoring in this picture, and that is the fact that once you ionize the hole, you ionize the dopant, you're left with a hole sitting on the pentacene and an electron sitting on the acceptor, and those are bonds. Those are coulombically bonds. And so if we take that into account, this coulombic binding, which is substantial, and we take into account the polarmonic effect, so the relaxation of the nuclei around the charge, then we end up with a situation where there is full ground state charge transfer. So if you look at the distribution here, these are the CT energies, ignoring electron-hole interaction. They are all on the positive side, no doping. If you account for the electron-hole interaction, if you account for the reorganization energy, you end up with this green distribution that is on the negative side, so this full doping. You can see that instead of having also finite levels, you get a distribution of levels, and this distribution is the disorder that is associated with the amorphous structure of the system and the associated energy distribution that you get in the CT pair energies. So in organics, the other ingredient I would like to talk about is this quantum mechanical interaction between the molecule that drives delocalization. And the type of system that we looked at to model this are fullerenes. So fullerenes, in principle, are very nice compounds to tackle that problem. They are extensively studied for inorganic solar cells, in part because of their high symmetry, and that sustains, that in principle should sustain high delocalization, because now you have a large, not only geometric connectivity between a molecule and its surrounding because of the spherical symmetry, but also a large electronic connectivity. And so we wanted to check or to quantify how much the charge, a charge that we inject into those fullerenes would be delocalized if we look at crystalline versus amorphous structures, or if we look at unsubstituted fullerenes with respect to the soluble version of the fullerenes. And so this is to address that question, you need to set up this Hamiltonian with your variation of the site energy to the polarization effects and all the quantum mechanical interactions. So we can do that. I won't go into the details of how we did, but you can do that and you can solve a problem, and you can look at the inverse participation ratio, which is a measure of how much the charge is delocalized in those systems. And essentially the answer is the charge delocalized or delocalized? I mean, it's both. It depends really very much on the energy. So you end up with an energy landscape that looks like this, so density of states, where the tail of the distributions, especially for the soluble version, are essentially confined over a single molecule. But that doesn't prevent the center of the distribution to have delocalization that can be up to 20, 40, or even more molecules. So then the question of localization or delocalization of those materials will depend very much at the energy at which you're probing. And so in principle, in equilibrium conditions for C60 derivative, for charge transport, you would probe the tail of the distribution. So essentially it would be a hopping model would seem appropriate. But I mean, if you can reach those the states in the middle, then you might take advantage of the extended delocalization of the electrons. And this is something that we believe that is happening if you look at organic solar cells, where you combine the fluorines shown here on the right with a polymer or a molecular donor. This is polythiophene, and so these are really modular systems of an interface between those for these donor acceptor junctions. And what is reported here is the CT energy as a function of distance between the electron and the hole. This should look something like a Coulomb law. And in fact, I mean, it doesn't really look like that. I mean, you see that's something that is really flat with a lot of on average, but with a large dispersion. And at short distance, you have then this strongly bonded pairs. So this is in a picture where the charges are, so we are completely localized. So what we do in those simulations, we force an electron to be sitting here, a hole sitting there, and we do the calculation and we repeat this over many realizations of the disorder to end up with this distribution. If you now allow for the electron to delocalize, you now include the quantum mechanical interaction for the electrons, or for both the holes and the electrons, then you see that the distribution is shifted towards larger distances. So essentially, you push the distribution towards this larger electron-hole separation values. So that meaning that, and you still get some lower energy states, but on average, you tend to favor states with delocalized hole and electron wave functions tailing towards the interface. This is important for This is important for the exciton dissociation process that turns out to be extremely fast in those structures with large energy offset. And this is because we are creating at the interface delocalized states with tails towards the interface. And you can see from this quantum dynamics simulation that the charge generation takes place over time scale that are very fast because of this extended delocalization. So delocalization in those states is important for charge separation, clearly. Now coming back to transport, I would like here to talk about two model systems that differ only slightly by the nature of the side chain. So these are peroline diimide derivative with either fluorinated side chains or completely alkylated side chains. And so those molecules can be prepared in single crystals that have been measured by Emanuele Orgio when he was in Strasbourg in a single crystal field effect transistor. And if you extract the mobility versus temperature from the transfer curves of the field effect transistor, you end up with something that increases steadily with temperature for that molecule, but that shows at least in this temperature window a band-like behavior where the mobility decreases when you increase the temperature. So this is a subtle change in the chemical structure that leads to apparently very different behavior in terms of the charge carrier mobility, which we wanted to understand. And so the first thing to realize is that the stacking structure of the two molecules is slightly different. It's more of a one-dimensional slip stack configuration for the in the alkyl case. So the molecules are slip stacked. They are not exactly stacked on top of one another, but slightly stiff. But essentially it's a 1D arrangement. While for the fluorinated side chains, there is also a little bit of H-pi interaction. So the system is more like a brick wall configurations where the transport can be two-dimensional. So you have quantum mechanical interaction in 2D versus 1D. So that's already one big difference. So what we do, we use the usual model with site energy depending on the environment, quantum mechanical interactions between all the molecules. You build large systems, large supercells of those crystals. You do molecular dynamic simulation. This is classical MD. And then you can solve this Hamiltonian as a function of time and track how the charge delocalize as a function of time. So this is a direct measure of the transient localization that we've heard previously. You can see how the charge breezes with time in the two molecules. And you can see that for the alkylated side chain molecule, there's large fluctuations around a small value. So the charge tends to be delocalized over no more than 2 molecules. For the fluorinated case, the average value is much higher. And this is partly because of the two-dimensional character of the transport, and also the yeah. So now you can ask yourself. I mean, there's the dimensionality issue, but also we know from and Henning has described this in very detail that those phonon modes, motion of the molecule with respect to one another, will ruin the transport properties. So we can ask ourselves, what are those killer modes? For this, first you need to get an handle of the description of all the phonons in the system, and you can do this by simulation of the inelastic neutron scattering shown here for the 2 molecules, and those compare reasonably well to experimental data, considering the fact that these are simple classical force fields. So the comparison is quite good. But so essentially, what this tells us is that we are able to reproduce correctly the phonons in those systems. So which phonon then dominates can be captured by tracking, for instance, the transfer integral between nearest neighbor. And we do this in a time domain. So you can compute the autocorrelation function of the transfer integral, and if you Fourier transform that autocorrelation function, you end up with a Flower spectrum, where the x-axis tells you something about the frequency of the modes that contribute, and the intensity is a measure of the electron-phonon coupling. And this shows the killer mode that Henning was showing just previously, except for the fact that it's rather more, it's a much richer spectrum that we get for those molecules. There are many modes that are involved. We can analyze those modes by doing just a normal mode calculation. And we see that they involve both longitudinal displacement of the molecule, lateral displacement of the molecule, rotational motion of the molecule. So all these modes seem to contribute, in that case, in those molecules, to give rise to large electron-phonon coupling, and therefore they act in concert to collapse the wave function and reduce the charge carrier mobility. Okay, now it's time to move to the perovskite. We talked about polarity effects in organics. Let's talk about polarons in perovskite. And there's a lot of discussion in the literature whether polarons can be seen in low-dimensional perovskites. Low-dimensional perovskite are particularly suited materials because of the confinement effects. They have strong dielectric and quantum confinement effects that in principle should allow you to see those polarons in a clear fashion. Now, we have to be very careful with literature data because often you can see from the emission of 2D perovskite like this one, this broad emission at a low energy that has been discussed to be of polaritic nature. One of the other possible explanations that we put up together with the Cambridge group here in this paper is that those emissions actually arise from color centers. I mean, ion migration is very easy in those materials, so you can have formation of, for instance, an iodine vacancy, iodine interstitial pair that will create trap states in the middle of the gap, and those trap states, we believe, are responsible for this emission. So you have to be very careful. But if you look at the optical absorption of a number of these two-dimensional systems, you see this very nice, sharp excitonic absorption that is shifted from the edge of the band gap absorption by what is the exciton binding energy, which is substantial, half an eV or so in those materials. And they are featureless. I mean, they are sharp and featureless. Really, to get to get an handle on or to be able to resolve a possible structure, you need to go to low temperature and use some specific techniques like the transient spectroscopy. This is work done by Carlos Silva on this 2D perovskite, where you see this is a pump probe technique, where you can see change in, I mean, you can see bleaching and excited state absorption appearing, but on top of this population dynamics, you might also be able to see on this picture here that there are some fluctuations. And so those fluctuations, if you subtract the exponential decay due to the population dynamics, you can see them more easily here. And you can see these quantum fringes, which are due to the fact that you prepare in the excited state, hot states, you prepare a vibrational wave packet that then evolves in time, giving rise to these fluctuations. And you can Fourier transform this to know something about which are the vibrational modes, which are the phonons that matter. And you can see that those appear at very low frequency. And we tried to model this using a very simple model. We took a large supercell of this 3D perovskite, computed the normal modes, distorted along the different normal modes, and calculated the electron phonon coupling interactions. And to our surprise, the blue line here is the calculated spectrum, matches quite well with the experimental spectrum. We see those four modes that are important, that modulate the band gap. And we can, of course, look at what they are. Maybe there's some animation here. So those modes essentially involve distortion of the octahedral configuration of the light inorganic system. And so those distortion, if you think in terms of displacement along the coordinates, they are substantial. So we talk about Uang-Quist factors to quantify this. So the Uang-Quist factors are pretty large. But of course, since we know we're dealing with systems where the reduced mass of the vibrations is much, much smaller because this is lead and it's not carbon, then the frequency is also much smaller, and the reorganization energy are typically one order or two orders of magnitude smaller compared to organics. So panoramic effects are rather subtle in those systems. No, last part of my talk, I will talk about 3D mixed halide perovskite, and the reason why I'm talking about this is because when I first encountered first heard about localization landscape theory, I thought this would be a nice system to apply that theory, because in a way it's not very different from gallium nitride system alloys. So, so in those systems, what you can do, so you see here the structure with the octahedral configuration of the lead halide. So you can change the composition going from either pure iodine to pure bromine. And it's also a nice way to tune the emission properties, as you can see from this graph, going from purely bromine to purely iodine. You get a strong redshift in the photoluminescence peak across more or less the entire visible. So this is a simulation done by Valentin here in the audience, looking at small models for those mixed halide systems, using periodic boundary conditions, of course. When E actually systematically tune or change the composition for pure iodine to pure bromine. You can see, quite surprisingly, there is a continuous evolution of the valence and the conduction band edge, and if you calculate the band gap, it follows quite nicely the experimental, or rather nicely the experimental result. But we were a bit surprised by those results because we thought that, okay, you start with a lead bromide, say, a pure compound, and this is a typical situation for the valence band of those materials. So you have strong hybridization between the lead 4p and the lead 6s and the bromine 4p orbitals, giving rise to the valence band H, which is this anti-bonding combination. And what happens when you introduce iodine 5p orbitals, because they have, of course, lower ionization potential, you might expect those to create traps, to act as impurities that would sit in the middle of the band gap. That is not the case, because essentially this energy level difference between the bromine 4p and the iodine 5p is smaller than the hybridization between the bromine and the lead. So this strong hybridization is one of the key features of those perovskites, and that's why they are rather robust against all sorts of disorder. And you can tune, of course, the composition as I showed, and look at the wave function. There is another feature, I think, that might not be present in the alloys, is that the orbitals are, even though you have a mixture here, a 50-50 mixture of iodine and bromine, you can see that there is contribution on the valence band H, for instance, on both the iodine and the bromine. So there's still interaction, hybridization through the different halogen atoms in the system, despite the energy difference. Now, of course, the picture that I showed is based on something that we can describe as being a solid-state solution, where to the scale that we're doing, that we're exploring, essentially the halide are homogeneously distributed, so randomly positioned. It could well be that in reality there is some degree of segregation, and for us this configuration would be extremely difficult to model, because that means going to a very large scale system, but we can certainly model a clean interface between the two, the bromine pure and the iodine pure layers. So what happens in a case where you have complete segregation? Well, that's a rather easy case, because what happens simply is that you end up with a two valence band model, one associated with the hybridization with the lead and the iodine at higher energy, and a deeper level, a deeper band that corresponds to hybridization with the bromine in blue here. And if you look spatially at the wave function, that's exactly what you find. So here we have the bromine layer, here the iodine layer. You can see for these two valence bands that they are either confined completely on the bromine or completely confined, or mostly confined on the iodine part. Now, between parentheses, this is something that we discovered recently, also with collaboration here with folks in Cambridge, with Felix Dessler and others, that this separation drives the formation of doping domains, and the formation of those doping domains that are physically separated is responsible for a change in the recombination and an increase in the luminescence quantum yield when you go from pure iodine to mixed iodine, and if you go from mixed iodine to if you have mixed cations as well, because those mixed cations, mixed organic cations, help you to get this phase segregation. So phase segregation is not necessarily a bad thing in those systems, at least in terms of the photoluminescence emission. Just a few words about energy disorder. So in those perovskites, so we heard a lot about Omec Energy already, and this can have different contribution. One is dynamic, will be temperature dependent. Essentially, will depend on the configuration, the conformational space or configuration space that the molecule can explore at a given temperature. There might be also some trapping contribution or an inhomogeneous contribution to the line width. What is really fascinating with those materials is that it seems that I mean, if you can do temperature-dependent measurements, of course, of the Omec energy, for instance, is shown here, and it seems that it goes down all the way to smaller and smaller value as you decrease the temperature. So it seems to indicate that the homogeneous contribution, the dynamic contribution, is really dominant. Although when you have mixed halides, this is shown here. This is not the full width at our maximum, but it's related to Omec energy. You can see that in the mixed case, the full width at our maximum is significantly larger than the values for the pure phases. And so this is something we would like to understand. So we have started those simulations. They are very expensive calculations. So these are Born-Oppenheimer molecular dynamics simulations, so quantum dynamic simulation, but with where we solve classical trajectories. And we track the energy band gap as a function of time. This is shown for MAPI for 2 different temperatures. You see those fluctuations in the band gap, which get, of course, much larger at room temperature because you have larger amplitudes of the motion. And so you can translate this into a spectral line shape with a certain width, and from this width you can extract, using this formula here, the Omec energy. So we did this for a number of systems, the purely iodine, purely bromine, and the mixed and segregated phase. These are very fresh data, so we still need to dig into the results in more detail, but what you see is, of course, the expected increase in the full width at maximum, increase in the Omec energy going from low temperature to high temperature. And at least if you go to the mixed case, if you focus here on this column, there's not a big difference if you compare the mixed phase compared to the pure phase, to the iodine or bromine pure phase. And the difference only shows up in a case where you get segregation. And we can discuss about the origin of that later on if you wish. But essentially, the effect of going from the pure to the mixed case is not that dramatic on the Omec energy. Now we're trying to understand where what are the phonons, what are the killer modes for perovskites, and you can do it in a similar way as I've shown for organic by working in a time domain and do the Fourier transform of any function. In this case, it's a band gap, and essentially we end up with something that again seems with a lot of activity here in the low frequency domain below 100 with numbers. This is a region where you expect longitudinal optical phonons in those materials, in those ionic crystals, to be very strong, and it's likely that some of these features correspond to those phonons. Now we need to study that in more detail, and for this, I guess, approach is like the one developed by Bartolomeo Montserrat would be useful. It's just interesting, just by exercise, to look at what happens in silicon. In silicon, I mean, all these features are gone essentially. There's no, it's completely flat, and you only have this low frequency tail that is due to acoustic phonons. Now, this is the kind of picture that we can look at in terms of wave function localization, and you will see that it's nice, but at the same time it's very frustrating because of the size of the system that we can handle. It's really difficult to conclude about the degree of localization or delocalization. And so, hopefully, with this information, with the electronic structure calculations that we've done, it would be possible to set up a localization landscape model, and we're looking forward to the interaction with Claude and Axel and colleagues to solve that problem. Yeah, just as a conclusion, yeah, maybe the difference between inorganic and organic is not that large. I mean, there's some overlapping features between those in terms of the mechanism that control localization, and maybe the magnitude of the interaction is different, but it's the same kind of physics. So with this, I would like to thank the people who've done the work. There's a lot of work done by Gabriele, Johan, Vincent on the organic part, and by Valentin, who is here, and Claudio on the lead-halide perovskite. And so we would like to acknowledge also a lot of interactions with different experimental groups. And thank you very much for your attention.